To day 10. It's been a little while since we've done a video, so welcome back. Today we're looking at two things, kind of the last two things that we're going to talk about before our first test. The first is units for derivatives, whether we're estimating them or calculating them ourselves, and average rate of change is what the two things we're going to look at today. So first, let's take a look at units for derivatives. Oftentimes, when we're just working with f of x and x, we don't have any units, so we don't have to worry about it. But there are times when we do have functions with units, and we need to consider what the unit would be of the derivative of that function. So to start, I'm going to do a problem that's going to relate to estimating a derivative, just so we can take a look at it. So go ahead and copy this table into your notes, and we'll talk about it. Okay, so here we have a table with t values on top and r of t values on the bottom. One thing to understand here is oftentimes people are way more comfortable with x and f of x or x and g of x, but oftentimes, especially rate problems, are given in terms of t and r of t. T here is going to operate just like x does, r of t is just going to work just like f of x. In the context of the problem, there'll be a big prompt here. I'm not going to write the whole prompt, but we do want to pay attention to the units given for both r of t and t. So let's say after reading the problem, t is given in minutes. So t's units is minutes. And let's say r of t is gallons per minute. I don't know what the context of this problem is. Maybe it's water leaking out of a tank, a pressurized tank or something. But we know that the rate, right, at time t equals 0 minutes, the rate is 100 gallons per minute, right? At 6-minute mark, we're having our rate be 36 gallons per minute. So what they might say is they'll give you some big prompt about some context of some problem. But they're going to say this: estimate r prime of 7.5. After they ask you to estimate r prime of 7.5, oftentimes in the free response they say something like include units, or sometimes you need to include units and give the meaning in the context of the problem. We'll work on the meaning later as we work with more of these functions, but let's just focus on the units now. Anytime they ask you for units on the problem, getting the units will be either worth a point itself, or you'll need to have the units plus the correct answer for 1 point. So again, units are very, very important here. Well, first, let's just go ahead and use what we know from our last video in terms of estimating r prime of 7.5. Let's forget all the things we need. We need the approximately equal to sign, or as I like to call it, the wiggly equal sign. We're going to need a difference quotient, and we're going to need an answer. And then at the end, we're going to have to put units. So let's do what we know first. Go ahead and find r prime of 7.5. Pause it for a second, and then go ahead and solve it. I'll go ahead and solve it too, and we'll talk about it. Okay, so taking a look here, I said r prime of 7.5, right? So we're looking for a t-value of 7.5. Well, that's directly in the middle of 6 and 9. So I'm gonna say that r prime of 7.5 is approximately equal to r of 9 minus r of 6 over 9 minus 6. That gives me a final answer of 4. Make sure you have your approximately equal to sign. Make sure you have r prime of 7.5. Make sure you have a difference quotient and your answer here. Now we need to figure out what the units are going to be. Okay? To figure out units here, let's just think for a second about what we're doing. Think about those numbers on top of the fraction. 48 minus 36. What were the units of those two numbers? Well, those are R of T numbers, and R of T's unit is gallons per minute. So I'm taking something in terms of gallons per minute, and then I'm dividing by that 9 minus 6. That 9 minus 6 are T values. They are in minutes. So my unit here, right, and for any derivative, I can solve this very simply by taking the units of y, or the units of f of x, or the units of r of t, whatever our function is, the y value, we take those y units and divide by the x units, or the t units. So in this case, I'm going to have kind of a convoluted fraction here of gallons per minute per minute. On the free response part of the test, they'd be okay with leaving a unit as gallons per minute per minute. Okay, but we can simplify that into something that looks maybe a little bit nicer. Now, one mistake people make, sometimes they think, oh, the minutes cancel, right? But if we think about what this would look like, we have gallons per minute divided by minute. If we think of both of these as a fraction, gallons per minute over minutes over 1, right? We know that we can get rid of fractions when we do a fraction divided by a fraction, we multiply by the reciprocal. So if we multiply both of these things by 1 over minute, we end up with 4 gallons per minute squared. So we end up going from R of t being a value of gallons, a unit of gallons per minute, to R prime of t here being 4 gallons per minute squared. Oftentimes what I like to think of is whenever we do a derivative and we have a time unit, we take whatever our unit was before and divide by a time unit again. So if I did another derivative, R prime prime, my unit would be gallons per minute cubed. Or if I did another one, I'd be gallons per minute to the 4th power. Okay? So we can always get our unit for derivatives by taking the y value and dividing by the x value, or taking the f of x value unit divided by the x unit, or taking the r of t unit divided by the t unit. Okay? So we want to be careful with that. Okay, so that's it for units of derivatives. We'll see more practice on that in class. The other thing I want to talk about is average rate of change. Oftentimes on the AP Calc test, they'll ask you in both the multiple choice section or on the free response section, they'll ask you to find the average rate of change of a function on a given interval. Okay? So they will give you that interval in a closed interval, and we're just going to talk about what that's going to look like. Okay? Average rate of change, the formula for this is very, very similar to how we estimate derivatives. Again, it just comes back to that really important concept of slope. So here's the formula for average rate of change. Average rate of change, I'll use ROC as an abbreviation, average rate of change on an interval a to b. I want to know of all the different slopes, right? Oftentimes we have functions that are nonlinear, so all the slopes of the tangent lines together. There could be infinitely many different slopes in there. We want to average all of them to know overall what is our average rate of change on an interval AB. Well, that's just the slope that connects from A to B. So again, the average rate of change, I'd say, of F on AB is F of B minus F of A over B minus A. Now, they could ask us this in terms of giving us a function, or they could ask this in terms of a table of values. I see it very often. Or they could even ask us an average rate of change given a graph. So maybe we'll look at one each. So let's start with using this formula for functions. So let's think about the function f of x equals 2x squared plus 1. My question is, what is the average rate of change what is the average rate of change of f on the interval of 1 to 5? So I want to know, what is the average rate of change of f on the interval 1 to 5? Okay. If you notice from our average rate of change formula, I don't have to do the derivative of f. I don't have to do f prime and find that f prime of x equals 4x. That's not even part of this formula. The average rate of change of f on that interval is simply f of b minus f of a over b minus a. One thing that helps is taking a look at this interval, 1, 5, and labeling this interval AB like we have in our formula. So go ahead and think about that. Our 1 here is going to act like the lowercase letter a, and our 5 is going to act like the lowercase letter b. So if I want to solve this, I want to say average rate of change of f on 1, 5. I'm going to say that average rate of change of f on that interval, 1, 5, that's simply going to equal f of b, which in this case is 5, minus f of a, which in this case is 1, right? I'm just following this formula right up here. And if you didn't already, go ahead and star that in your notes. It's a formula that's going to come in handy. We're going to use it a lot. So the average rate of change of f on interval 1, 5 is f of 5 minus f of 1 over 5 minus 1. Now we're not quite done. We want to figure out what this actually is, but it's going to be really easy to work from this with this from now on. Also, notice average rate of change isn't an estimate, so we can use a regular equal sign in between in our equation there. This is definitely a exactly equal to. It's not an estimate like in the last lecture. Okay, so let's see what happens when we plug in, right? All we have to do here is plug in 5 into f, plug in 1 into f, subtract them, and divide by 4. So I need to think, okay, what is f of 5? Right? I'm just going to plug in 5 for x. 5 squared is 25. 25 times 2 is 50. 50 plus 1 is 51. Minus f of 1 would be 1 squared is 1. 1 times 2 is 2. 2 plus 1 is 3. And I end up with 51 minus 3 over 4. Simplifying that out a little bit more. 51 minus 3 is 48. 48 over 4 is 12. So the average rate of change, the average slope from all the points between 1 and 5, the average of all of those infinitely many things is 12. That is our average rate of change, and it's simply the slope that connects the 2 points on the graph. Okay. Also notice, did I give you any units for f of x and x? We didn't. The units for average rate of change will be the same as our units for our derivative. So when we look at it in a table, I'll give you some units to work with. Okay? But our average rate of change of f on 1,5 there is 12. Let's try it in table form. Okay, so I included in this table here the units. So I just put sometimes I put the units right in there. So our top letter is T there. T is going to be measured in seconds here. That S is for seconds. Maybe I'll expand that so it says seconds instead of just S. So T is measured in seconds. P of T is measured in liters. Okay? Now I could ask you to estimate P prime of different values here. Okay? But what I'm going to ask you, and you should know how to do that, I'm going to ask you now, what is the average rate of change of P on the interval 0 to 12? Take a second and think. Imagine that I asked you to find P prime of 2, right? To do P prime of 2, we'd end up doing 6 minus 15 over 4 minus 0, right? And we'd get an answer. What would be the units of P prime? Well, P prime's units would be our P of T unit divided by our T unit. So P prime's units would be liters per second. We're going to end up with the same exact units for average rate of change. Because again, they're both relating to the slope of the line. And to find the slope, we take the y units divided by the x units, or in this case, the P of T units divided by the T units. So if I want to find the average rate of change of P on this interval 0, 12, okay, this is going to equal, right, this is our A, this is our B. So this is going to equal P of B minus P of A over B minus A. Well, since we know B is 12 and A is 0, this is going to be P of 12 minus P of 0 over 12 minus 0. You don't necessarily have to write that first step there of P of B minus P of A over B minus A. I just wrote that there to remind us that we're using our average rate of change formula. In this case, A is 0, B is 12, so you can go right to P of 12 minus P of 0 over 12 minus 0. Well, P of 12 we know is 60. P of 0 is 15, so I'll have 60 minus 15 over 12. 60 minus 15 is 45. And when we reduce that fraction of 45 over 12, we get 15 over 4. But we also need to consider the units here. We're also going to say include units. So 15 over 4 is our average rate of change here. We have to consider the units. It's the same units as what p prime would be. We want to take the y variable divided by the x variable, which is liters, divided by seconds, and we get liters per second. And there's our answer. So that's table form. I want to do one more quickly in graph form. Okay, so let's take a look at this graph here, and let's take a look at the y-axis and the x-axis. The y-axis here is v of t. The x-axis here is t. So this is a velocity graph. Obviously, we're measuring velocity here in meters per second, would be the unit, and our time here is being measured in seconds. So let's think about those 2 points we have here. Go ahead and label this point 2, 3. And go ahead and label this point 12, 8. Again, here's the question. I want to know the average rate of change of velocity on the interval 2 to 12. So I want to calculate, what is our average rate of change of velocity on 2 to 12? Now, if you think back to your physics knowledge, we'll talk a lot more about this year, but what is the rate of change of velocity? What would that be? Think about it. Well, the answer is, obviously, acceleration. The rate of change of velocity is simply acceleration. Acceleration is delta v over delta t. Or you can say the slope of a velocity graph tells you the acceleration. Well, we want to know the average acceleration, or the average rate of change of v on this interval. Well, as we can see, if we looked at the tangent lines, there's all kinds of different stuff going on here. We have positive tangent lines, we have zero tangent lines, we have negative tangent lines, we have another zero tangent line, we've got some pretty positive ones. What happened if we average all those tangent lines together? Well, it would equal the slope of the line that connects those two endpoints. So that secant line that connects 2, 3 to 12, 8, the slope of this equals the average rate of change. On that interval. So again, if I want the average rate of change of velocity on the interval 2, 12, this is simply going to be, again, here's my A, here's my B. This is simply going to be V of 12 minus V of 2 over 12 minus 2. Well, what is V of 12? V of 12 is 8, right? I'm doing my change in Y. 8 minus 3 over 12 minus 2. 8 minus 3 is 5. 12 minus 2 is 10. So I get an answer of 1/2. But again, I want to consider the units here. Now again, the easy way to do this is just take the units on our y-axis and divide by our units on our x-axis. Meters per second divided by seconds. And if we simplify that, we see we end up with meters per second squared. Now this should totally jive with your physics knowledge because we know that the unit of acceleration is in meters per second squared, or feet per second squared, or miles per hour squared. So again, it should match with that. That's all for today. We'll check in tomorrow, go over this. Have a good one.